does join in. There's 12 currently. But I am going to put on another session next week on Thursday, and it'll be the same time. So currently it's today, obviously Wednesday from 10 till around 11:30. I'll see how that goes. Might extend it a bit or shorten it a bit depending on where we're at. Then next Wednesday from 10 till 11:30 as well. But I'll also do next Thursday, I think, from 10 till 11:30. Just after looking through a couple of things. Actually, would somebody mind just throughout these classes, by the way, you can just turn on your mics to ask a question. That's definitely the easiest way for me to follow what's really being asked. Or you can type it in the public chat, or you can click on my name and send a private chat. But would somebody mind letting me know, do ye each have, because I've only been sent on a few things that Epistem sent me on, do you each have 3 tutorial sheets and solutions, and I have the last 2 exam papers? Is that what you guys have? Somebody mind just letting me know? Yeah, okay, perfect, thanks. Grand out. Okie doke. Do you have solutions to those exams? Maybe, maybe not. Okay. Undecided. Okay. Give it another 2 minutes. Okay, folks, I'll make a start. The slides for this, so you don't have to take anything down. Maybe you have the solutions anyway. I don't know. But I might be filling in a bit more information. The slides I'll be putting, so where we put up our videos for this module last week, I put them up on our Solus site where you joined this class. If you scroll down the left, there'll be MB5003 24/7 support. I'll put the slides in that. So if you drop that down, you'll see I'll put like revision slides or something. So I'll be putting the slides in there after the class. All right. So don't worry about taking down too much. Obviously, if there's certain things you want to take down, do. But I'll be putting up the slides afterwards. I've allowed you to join with your mics. I just appreciate if you could mute unless you have a question to ask. Obviously, unmute and ask away. So just a tiny bit of housekeeping. We don't see any exams that you guys take or anything like that. So that this is in no way a prediction of anything. I'm just covering. Epistem sent me on two exam papers and 3 tutorial sheets last week. I haven't seen your lecture notes or anything like that. So I'm just basing it off of that, and I just picked one of the exam papers. I'm also going to have class next week on Wednesday and Thursday. So in the email that Epistem would have sent you, it didn't say Thursday, but I think I'm going to do Thursday as well. Just because I feel like some of the background stuff, maybe partial differentiation and that, might have to go through that a bit slower. And I don't want to be rushed either. There's no point in that. So just note that as well. The next Thursday will also be here from 10 to 11. Same joining instructions as today's one. If you can, as much as you can, try your tutorial sheets and the 22-23 exam, the other exam paper, in advance of next week, as much as you can. I'll ask on Wednesday and see which of the 2022-23 questions and maybe some tutorial questions that people would like to try and cover on the Thursday. I'll try and fit in as much as I can. So try and have a go at as much as you can before then. And as I said, I kind of asked that already, and someone responded. So hopefully you have the past paper solutions, though. I don't know if you have those or not. Other than that, we'll get started. I said to the group that were here earlier on, a couple of minutes ago, if you have questions throughout, you can throw on your microphones. That's no problem whatsoever. I just appreciate if you kept them muted until you were asking something. You can click on my name and send a private chat to me, or you can type a question in the public chat. Microphone is easier for me to kind of understand what the actual question is, but feel free to ask whatever you want. So that being said, this is the first question in the 21-22 exam. It said find the directional derivative of f. So we've a function f given in the question at the point 1, 1, 2 in the direction of the vector 3i minus 2j plus k. And here is the form of the formula you're using for directional derivative, and it's this here. So we're going to need to find del f, which is the gradient of the scalar field f, and it's dot producted. Dot means a dot product with the vector u. Now, it's not just a random vector, like this is in the direction of this, but it is in the direction of the unit vector u. Okay, so as I said, if you wouldn't mind just keeping mics muted, just there's a bit of yeah. Okay, so if this is the vector u, let's say, and that's the only vector given in the question, 3i minus 2j plus k, like that is not a unit vector, because if I take the magnitude of that vector, just a quick recap, just change this up from red. Red is not very nice. The magnitude of a vector is the square root of all of the components to be squared. So 3 squared, and we add them up, plus minus 2 to be squared, plus k, well, the coefficient of k there is just 1. Any variable on its own or little vector unit on its own is just 1 times k, plus 1 squared. So the magnitude of the vector given in the question, the square root of 3 squared is 9, plus 4 would be 13, plus 1 will be 14. So the magnitude of the vector given in the question is root 14. That is not a unit vector. A unit vector has a magnitude of 1, right? That's a unit vector, 1 unit. So we're going to need to find what is the unit vector u hat. Now, I mean, just logically speaking, if you take a vector and divide it by its own size, it'll give you 1 unit. So that's exactly how we find the unit vector. So the unit vector in the direction of this one will just be that vector. I mean, you have a formula for it. It'll say u divided by the magnitude of u. And we just found the magnitude of u. So I'll take the vector, 3i, I'll just use the pointed brackets notation, 3i minus 2j, 1k, and I'll divide that by its own magnitude. So the unit vector, well, to divide them, I'm literally going to divide each of them by the magnitude. So I have 3 divided by root 14. I have minus 2 divided by root 14. And I have 1 divided by root 14. So that's our unit vector for our formula. There are quite a lot of formulas in this kind of material. You're going to have to go through the lecture notes and note them down. Probably my advice for this evening is go through the lecture notes if you haven't done so. Write down all the formulas and learn the ones you need to learn. But that's our unit vector u for the formula. I also need to find the gradient of f, or that upside down triangle is del, D-E-L. So del f, or the gradient of f. I also need to find that. So the gradient of f is the first partial derivative of f with respect to x, curly d's, the first partial derivative of f with respect to y, and the first partial derivative of f with respect to z. Now, I'm just going to write down the function. At any point you have questions, please do pop them in. Just, you get out you get more out of it if you ask the question. But we need to partially differentiate that function with respect to x. We need to partially differentiate that function with respect to y, and we need to partially differentiate that function with respect to z. And then afterwards, sure, we have a point that we can fill in, but firstly, we have to do that gradient of f calculation. So I'm just going to take it aside for a second, and let's say I was differentiating that partially with respect to, let's say, x. So when we're partially differentiating with respect to one variable, let's say x, as I've just written, we treat any other variable as if it's a constant. So in my head, because I'm partially differentiating with respect to x, I am treating this function as if it's like 2x times 3. I'm treating y, I'm pretending that y is just some constant value in my head. I wouldn't write that down, but that's what I'm doing mentally as I'm trying to calculate this. Because I'm partially differentiating with respect to x, I am treating any other variable, here there's just y, as if it's just some number. Now you could say, sure, 2 times 3 is 6. So this would be like differentiating 6x. If you differentiate 6x, you differentiate that just normally with respect to x, you get 6. If you differentiate 6x, you're just left with the constant. So here, if I partially differentiated this with respect to x, differentiate the x term, I'm just left with the coefficient. I'd be left with 2 times 3. In the context of, like, this is actually what it is. It was y. I'm just pretending that y is a number. When I partially differentiate with respect to x, treating y like a constant, so I have 2 times x times a constant, I'd be left with 2 times the constant. That's just a quick kind of revision on partial differentiation. If I partially differentiated the example, this is just a side example, with respect to y, I go back to my function, I'm differentiating this partially with respect to y, so I am treating x as if it's a constant. So I'm going to treat this as if it's like 2 times 4 times y. Well, if I differentiated 2 times 4 times y, I'd be left with 2 times 4. And as I said, x was the one that I was pretending to be 4, so I'd say it's 2 times x, which are kind of mentally treating it as if it's just some number, right? And I know that's only a quick 2xy example. Here we have to partially differentiate something that looks a bit more complicated, but that, like, mental picturing of, let's say if I'm partially differentiating with respect to x, I'm treating y as it's a y and z, sorry, as if they're numbers. If I'm partially differentiating with respect to y, I'm treating x and z as if they're just numbers. If I'm partially differentiating with respect to z, I'm treating x and y as if they're just numbers. You just treat the other variables as if they're just some constant. Let's go ahead and try to partially differentiate this with respect to x, because that's one of the things that we need. So when I'm partially differentiating xy with respect to x, I am treating y as if it's a constant. So I'm treating this as if it's like 3x. Well, what would I get if I differentiate 3x with respect to x? I get 3. So if I differentiate xy partially with respect to x, I just get y. That would be that one. That would be the derivative of that term with respect to x. Differentiate y cubed partially with respect to x, as I said, when I'm differentiating with respect to x, I'm treating y as if it's a constant. So I'm treating this as if it's like 4 cubed, right? Now, 4 cubed is 64. If you differentiate the value of 64, differentiate any constant, you get 0. So when I partially differentiate just a y term with respect to x, because I'm treating y like it's just a number, it will go to 0. I can write that down if I want, just for following's sake afterwards. If you're just joining in, I'm putting these slides afterwards into the MLC Solus site where you join this class. Go down to MB5003 and I'll put like a subfolder in there called revision slides. I'll be putting the slides in there. Partially differentiate with respect to x minus 3z squared. I'm treating z as if it's a constant as well, because I'm partially differentiating with respect to x. X is the only one I'm treating like a variable. So this is like minus 3 times 5 squared in my head. So that would be like differentiating minus 75. If you differentiate a constant, you get 0. So the first partial derivative with respect to x is just y. All right. We're going to go through the exact same kind of mental approach. When I'm partially differentiating with respect to y, I'm treating x and z as if they're constants. So this is like 6y. If I differentiate 6y, I just get left with 6. So I differentiate xy, I'll just be left with x. Differentiate y cubed with respect to y. Well, that's just differentiating normally. There's no x's or z's in it. So I'm not treating anything as if it's just a constant. So differentiate y cubed, I multiply down by my power, just normal differentiation, and I subtract 1 from the power. Differentiate minus 3z squared with respect to y. Differentiate with respect to y, treating z like a constant. It's like minus 3 times, as I said, 5 squared or something. That will go to 0. So my first partial derivative with respect to y is x plus 3y squared. I haven't met you before. I'm trying to go through partial differentiation as slowly as possible, while still trying to get the thing done. Can I just ask? I'll just keep it as simple as I can. I'm just going to run a poll. Is the likes of going through partial differentiation, as I said, as slowly as I can within trying to cover the paper, is the likes of that helpful, or is it needed? Yes. Okay. Lovely job. That's fine. I'll keep doing that. So sorry, I just haven't met you before, so I'm trying to get a grip on. Okay. Thank you. Right. So the last partial derivative I need is the function with respect to z. So differentiating with respect to z, I'm treating x and y as if they're constants. So treating x times y, I'm treating both of them as constants. It's like 3 times 4, which would be 12. If you differentiate 12, you get 0. So the first term will go to 0. Differentiate y cubed partially with respect to z. I'm treating y like a constant. So it's like 2 cubed. If you differentiate 2 cubed or 8, you get 0. So that second term will also go to 0. Differentiate minus 3z squared with respect to z. There's no x's and y's in it, so I'm just going to differentiate it using normal differentiation, multiply down by my power, and subtract 1 from the power, because there is no x's and y's in it. So it'll be minus 6z to the power of 1, or minus 6z. So that's all our partial derivatives for the gradient of f, or del f. I'm asked for the directional derivative of the function at the point 1, 1, 2. So I'm going to go ahead now, and I haven't structured this slide very well, sorry. I'm going to go ahead and work out, well, I can write the gradient of f using my formula. It's for that, it's del f del x, which is just y. Del f del y is x plus 3y squared. And lastly, del f del z was minus 6z. Question or just someone joining? 2 seconds. Someone joining. So I'm looking now for that at the point 1, 1, 2. this notation just means whatever we're evaluating, that vertical line just means at the point 112. I'm just doing that for tidiness or space sake. So at the point 112, well, I have a y thing here. A point is x, y, z. So our y value will be 1. So I'll just sub that in for y. For our next one, I have x plus 3y squared. The x value is also 1. So I'll be subbing in 1 plus 3. The y value is 1 squared. And our last one is minus 6 times z. Our z value is 2. So minus 6 times 2. So that equals, well, 1 is on its own. I have 1 plus 3 times 1 squared is 4. And I have minus 6 times 2 is minus 12. So they're my bits of information for the formula. It says that the directional derivative of f in the direction of the unit vector u equals the gradient of f, and I've evaluated at the point that I'm asked, 1, 4, minus 12, dot producted with the unit vector u, which I already worked out over here. So 3 over root 14 minus 2 over root 14 and 1 over root 14. So I need to just work out that dot product now to calculate the directional derivative. I'm actually going to take down just on the next slide here. As I said, this is just a separate example of partial differentiation. So write it down. It was 1, 4 minus 12. That with 3 over root 14 minus 2 and 1. So dot product of two vectors, you multiply dot product. Another word for a dot product is a scalar product. We should only be getting a number out of this as our answer. We shouldn't be getting a vector. A dot product gives us just a value back. So how we calculate it is we multiply the two I components together. So 1 times 3 over root 14 plus we multiply the two j components together. So 4 times minus 2 over root 14 plus we multiply the two k components together. So minus 12 times 1 over root 14. And we work each of those down. 1 times 3 over root 14. 3 over root 14. Plus by minus is minus. 4 2s are 8 over root 14. And plus by minus, 12 times 1 is 12. So in total, we have minus 17 over root 14. Use a calculator if you're not too sure, obviously, of those calculations. But that will be the answer to that question. All right. I'm not going to go through partial differentiation every time. There will be a lot of it in this module because of the nature of its multivariable calculus. So when you're differentiating with respect to a lot of different variables, you would be using partial differentiation. So that's why it's going to crop up quite so much. But just for the first crack of it there, I said I'd do it. There's 30 here. No, I think 8 people have watched the 24/7 support so far. I do kind of direct you to that as well. I've put in some videos just on partial differentiation. If it's something you need to revise, maybe work through as much of those as possible. They were developed for engineers specifically, hence why some of the notation is different, but a lot of the problems will be quite similar. That was question 1A. Question 1B, say questions, pop them in the chat, private chat, public chat, turn on mics, whatever. Okay, as many questions as you can would be beneficial. Question 1B says to consider the function. So we're given some function. That's actually the same as the last one. And we're told that this function has a local linear approximation, and we're given that approximation at the point x0, y0, z0, and we're asked to determine that point. Now, this is a more complicated question. I had a look this morning at the paper just from the summer, the more recent one, and this is a more complicated version of question 2b in that paper, because you were actually told the point and everything in 2b in the summer just gone. So this is a more complicated version because we're asked to determine the point. So again, we have this long formula. You're going to need to know that formula. But let's take it bit by bit and try and simplify down as much as we can. So this here means the first partial derivative with respect to x. That is exactly the same as this. So we've seen the likes of that. Likewise, just in case you're not fully sure, this is the first partial derivative with respect to y of the function. They're the same thing, they're just written slightly differently. And this is identical to this. All right, it's just for shorthand, it's easier to type the likes of that. So we're told consider the function, it has a local linear approximation as given, and determine the point x0, y0, z0. So we don't actually know the values of any of these in the formula, and we're asked to find them. All right. Unlike the paper just gone in the summer, you were told what those values were. So it was maybe a slightly easier problem. But let's go ahead and start working through as much as we can. Like, this is the value of the function when x is x0, when y is y0, and when z is z0. When we don't know those values, like, all that I can literally do to find that for the formula is to substitute in x0 instead of x in the function, y0 instead of y in the function, and z0 instead of z in the function. I can do no more than that. So it's xy, so it'll be x0, y0, plus y cubed is y0 cubed, minus 3z squared will be minus 3z0 squared. That's all I can do to substitute them in. I don't have values for x0, y0, and z0. This part of the formula says the first partial derivative of f with respect to x at x0, y0, z0. Well, the first partial derivative with respect to x, it's the same function as the previous one, isn't it? So, yep, so we can just use that. It was y. So that was the first partial derivative with respect to x. So that evaluated at x0, y0, z0. Well, all I can do is substitute in x0 instead of x. I don't have any x there, so I won't replace anything with x0. y0 instead of y. So instead of y, I'll put in y0, y0, and z0 instead of z. Again, I don't have any z here, so I won't replace anything there. Okay. My first partial derivative with respect to y, we worked it out previously. I'll just do it out quickly here. So it'll be, that's what we had. So the first partial derivative with respect to y at x0, y0, z0. Again, replace any x with x0. Replace any y with y0. And replace any z with z0. But we don't have any z over here. So we've taken care of that. The last one that we really need for now is this. So the f of z. Again, that was my first partial derivative with respect to z. Previously, we had minus 6z for that. So that evaluated at x0, y0, z0 will just be minus 6z0. So that's pretty much all that I'm at with regards to this formula, right? So filling them in, I would get the delinearization, or L, I meant to write. Sorry about that. X, Y, Z equals. So the f, the function evaluated at x0, y0, z0, that's the best I could do with it. x0, y0 plus y0 cubed minus 3 z0 squared plus the first partial derivative of f at that point was just y0. And that's multiplied by x minus x0. So again, x0 is x0. I'm not given a value for that, so I'll just write it like that. X minus x0. First partial derivative with respect to y at that point was x0 plus 3y0 squared. So x0 plus 3y0 squared. And I'm multiplying that by y minus y0. And if you had a y0 value, you'd plug it in there, like in the previous summer, just the one just got. Last piece that we need to put together is f of z at the point was minus 6z0. And I'm multiplying that by z minus z0. Clearly, the formula is very important. You need to know that formula. So, is there any bits of tidying up and all that I can do? Well, look, I'll just multiply it out and see. So y0 cubed. Yes, the first few terms there are just staying the same. I have y0 times x is y0x. I have y plus y0 by minus x0 is minus x0 y0. Plus, I'll multiply out this bracket separately. So x0 times y is x0y. x0 times minus y0 is minus x0 y0. 3y0 squared times y is 3y y0 squared y. And 3y0 squared by minus y0 is minus 3y0 cubed. y0 times its y0 squared times y0 is just y0 cubed. y0 and y are not the same, hence why these two stay separate. They're not, algebraically we call them like terms. They're not like terms, they're two different terms. So multiply out those two brackets. Lastly, plus by minus is minus. 6z0 by z is 6z0z. Again, they're not like terms. Plus by minus is minus. 6z0 by, minus by minus is actually a plus. Sorry about that. 6z0 by z0, they are like terms. So z0 times itself is z0 squared. All right. So, right, let's keep going with that. I mean, is there anything else we can do? There will be. Okay, so I'm gonna just keep going at the algebra of that. Hopefully I'll be able to track it from one slide to the next. x0, y0 plus y0 cubed. And like literally all I'm doing so far is just, once I've filled into the formula, I'm just doing algebra, just to try and tidy things up. I mean, we try to make things as tidy as we can before we do anything else with them. Plus y0x. Minus x0, y0. I'll multiply this plus into the bracket. It's not going to change any signs. I'll have plus x0y. I have minus x0, y0. I have plus 3y0 squared y. Do sex there now, like that. Minus 3y0 cubed. And then I have minus 6z0z plus 6z0 squared. Z0z on that? Yeah, plus 6z0 squared. Oh, that's the kind of, I'll tell you that up in a sec. Yeah, there's someone with their hand up there. Yeah, Laura. Don't know if you have a mic available. No. you want to type it in, or because sometimes this is quite hard to change from a headphone to a mic. Yeah, there's somebody else with their hand up just when maybe while Laura's typing in. Okay, oh, there you go. No worries, no worries. I'll get a beep in my ear when a chat comes up, so I'll come back to I'll just tidy this up very slightly. If there is a question, I'll come back to it. I can see I've x0, y0 minus x0, y0, so they'll cancel. Any term minus itself basically is 0, they'll cancel off. What else do we have? I have, is there any other like terms there that we can see? I don't think so. So we can write that as, oh, actually, just before we go that far, what are we trying to get to here? Like, I know that the linearization, that the x coefficient is 3, right? I know the x coefficient has to equal 3, right? So likewise, I know that the y coefficient has to equal 29. Likewise, I know the z coefficient has to equal 6. And likewise, I know that all the constants have to equal minus 57 when I piece it all together. So we might actually be able to kind of go with that from here. Like, here's x. It's not x0, it's just x. So I know that the x coefficients, just try to box them off. I'll write it here, x coefficients. I'll put them all together and see. The x coefficients are y0. Is there any other x hanging around here? Nope. That's the only x coefficient. You can see that, sure, there is some x zeros in there, but there's no just x on its own as far as I can see. So the x coefficients, it's just y0 is the only x coefficient. I know that all the x coefficients in total have to equal 3. So in other words, y0 has to equal 3. That would be our value for y0. Let's go back to our linearization again. All the y coefficients have to equal plus 29. So all the y coefficients which, let's see where they are. There's y0, that doesn't count. x0 is a y coefficient. 3y0 squared is a y coefficient. So the two of them together, x0 plus 3y0 squared, have to equal, what do we say, 29. We know the value of y0 is 3, so let's sub that in. And we'll be able to solve that for x0. Oops, plus, all right, plus 3 squared, that's 27, plus 29. So x0 is 29 minus 27, which is 2. That's our x0 value is 2. Going back again, our z coefficients have to equal 6. So we'll track through and we'll go for our z coefficients. I might just change up the color of this one. Probably should have done that last time as well. Z coefficients. So I'll track through my equation up at the top. There is a z coefficient here. And that's it. So minus 6z0 is the only z coefficient. We know from our linearization that that has to equal plus 6. So solving that for z0, z0 will be 6 divided by minus 6 plus over minus 6 over 6. So that's our z0 value. Now that's the coordinate that we were asked for. We were asked to determine the point x0, y0, z0. But now we will just do one further check. x0, y0, z0 equals our x0 value turned out to be 2. Our y0 value up the top turned out to be 3. and our Z0 was -1. As I said, we will just go through one final check just to be sure that we're right, because the last thing that we said was all the constants had to equal -57. So if I take the constants here, remember y0 is just a value, we're saying now what it is. It's not y or x or z, it's y0. So y0 cubed, 0 cubed, minus 3z0 squared. There was a y, x, minus x0 y0. That's a constant in the context of this. There's a y in that one, so that's not a constant. Minus 3y0 cubed is a constant, and plus 6z0 squared. That all of them together should equal minus 57. So we need to check that. If do they equal minus 57? When I sub in these values and they do equal minus 57, I know they're the right values for the linearization. So y0 cubed, y0 I'm saying is 3, minus 3 times z0 squared, z0 is -1, minus x0 times y0, minus 3 times y0 cubed, plus 6 times z0 squared. Oh, get my calculation hat on. So 3 cubed is 27, minus 3 times 1 is minus 3, minus 6, minus 81, and plus 6. So I have 24 minus 6 is 18, and 6 is 24, minus 81 is minus 57. So because they equal minus 57 when I substitute in those values, I know that the three values are correct. So that will be the coordinate that I was asked for. All right. As I said, the one in just the summer just gone previous, in my opinion, it is an easier question. But if you have the solutions to that exam paper, when you look through the one just gone, it was question 2B. You were asked to determine the linear approximation. So it would just be a case of, if I go back to the formula, I was given the point in last year's, it was just -1, 3. Now that's just x and y, and you can see the function in that paper just had x's and y's in it. So I actually wouldn't need this part of the formula, because that's the one that deals with z's. So for the paper just gone, I only really needed this bit. And I'd be subbing in -1 for x, for x0. Model myself now. -1 for x0 and 3 for y0. So you literally plug it in to the function that you were given. Sub in -1 for x, 3 for y0. You'd find the first partial derivative with respect to x. Sub in -1 for x0 and 3 for y0. Likewise, x minus x0 would be x minus -1. First partial derivative with respect to y, you'd sub in -1 for x and 3 for y0, y minus 3. And you would work that down and it would give you the linear approximation. So if you do have the solutions, when you follow that, that's what you'll see is happening. You won't see any z's in it because it was just given as an xy. The previous year, this one, I think, is a bit more complicated. But anyway, that's 1B. Questions, please do shout. Question 2, this particular year says, write down a vector valued function that, joining or leaving or, okay. Write down a vector valued function that represents the line segment. Now, a line continues forever, infinitely, in both directions. A line segment is just a specific section of a line. So I'm just going to have that in my head. It's a line segment from 301 to 51 minus 3. The vector value function, we're essentially looking for the vector form of this. And this is my notation. Maybe the notation in your lecture notes will be different. But the vector form of a line is r of t, so some parameter t, equals r0. Simplest way I can put that is it's a position vector on the line, i.e. a point on the line written as a vector. So I'm going to say r0 here. is, well, here's, let's say, the first point on this line segment. I'm going to say R0 is that written as a vector, using pointy brackets as opposed to round brackets signifies a coordinate, pointy bracket signifies a vector. That's R0 plus V0t. T will be in the answer in the vector form, but V0 we have to find. Now V0 is the direction vector. If you have some vector A, G, vector A, let's say 1, 2, 3, and a vector B saying 4, 5, 6, then the vector connecting them, which is the direction of this line, like the direction of this line would be the vector connecting this one and this one, if they're both on the line segment. The vector connecting them, the vector AB, is given by the vector B minus the vector A. You would have seen that probably in calculus 1, I'd imagine. And you literally subtract the vectors. Minus the vector A, 1, 2, 3. To subtract two vectors, you subtract the like terms. So 4 minus 1, 3, 5 minus 2 is 3, and 6 minus 3 is 3. Could have picked better examples for digits there because they just all ended up being 3s. But V0 is the vector connecting the 2 points on this line. Note in my formula, it's the vector B, which is like the end position, minus the vector A. So my V0 will be like that final position. It's supposed to be a 5, not a 3. Five, 1 minus 3 minus the initial position. That will give us the direction of the vector connecting both of those. It will give us the direction vector, I should say. Subtracting two vectors. So the first one will be 5 minus 3. Second component will be 1 minus 0. Third component will be 3 minus 1. Sorry, minus 3 minus 1. So we get 2, 1, minus 4. So that's V0. So in total then, the vector form of my line, R of t equals R0, which is 3, 0, 1. That's just the initial point, let's say, plus V0 times t. V0 is 2, 1, minus 4 times t. Now, for the most part, we kind of simplify these again as just to throw them all as like in one set of pointed brackets with commas in between them. So I'll do that step by step. I'll keep the first one for now. And I can multiply all of these by t because they're multiplied by t. So 2t. 1 times t is 1t, or just t if you want. Minus 4 times t is minus 4t. And now I have the addition of two vectors. So I have 3 plus 2t would be the first component. The next one would be 0 plus t is just t. And the last one is 1 plus minus 4t. Well, plus by minus is minus. So 1 minus 4t. Now, anyone brave enough maybe to put it into the chat? Don't mind if you're wrong, if you try answer if you're wrong. What's the last thing I really need to consider here? There's something else I need to include. Goes back to the first sentence, I underlined something. Line segment, exactly. The form that I have here, right, technically goes on forever. If I subbed in t equals to 100, I'd get 203 comma 100, comma minus 399. Now, that coordinate would certainly not be on the line joining both of those points, right? So I need to define this for values of t that will start at this point. It will start the line at that point, and they will end at this point here. So I can see that, like, when t is 0, 3 plus 2 times 0 is 3. Let's say when this is just extra stuff. When t equals 0, this point here will be 3 plus 2 times 0. When t is 0, that would give 0. 1 minus 4 times 0 is 1. When t is equals to 0, it would give me that starting point. So how far do we need to go up then? Well, when t is 1, I get 3 plus 2 times 1. And t is 1, and t will just be 1. 1 minus 4 times 1 is minus 3. So when t is 1, I'll get the end point. So I need to state that they're the values of t. Let's say for. So this would be my form of the line segment. Now, look, maybe those ones might be okay to see. If you're not sure about the t values, you can solve for them. We'll just do it on the next slide, just to make that a bit clear. Maybe I didn't make that clear enough. Like, here was my end point of the thing, but as I said, that's an infinite line. We do need to define t's if it is just a line segment, if it is not a full line. If that said, find a vector value function that represents the line connecting those 2 points, not a line segment, but a full line that just runs through, I suppose, both of those points, then this will be totally fine. But if it's just a line segment connecting the two, I need to start and stop it at certain values of t. So I know this needs to start. How was it? 301, 301. And it needs to start at that point. So I could say, well, at the start point, this has to equal 3. So 3 plus 2t has to equal 3. And I could solve it for t. 3 minus 3 is 0. So t equals 0. That's the value of t that will start it. And I can check then, like, if I do sub this in here, 0, yeah, that gives me this one. And if I sub in 0 in here, 1 minus 4 times 0 does give me that one. So that's definitely the starting t value. Likewise, I know it needs to end at 5, 1, minus 3. So I'll do exactly the same thing. I mean, the easiest one to solve is just picking, well, it needs to end when t is 1, just by solving the middle one. But you could pick any of them. Pick the first one. 3 plus 2t has to end up equaling 5. So 2t will equal 5 minus 3 is 2. So t will equal 2 divided by 2, which is 1. As I said, you would get exactly the same thing if you just followed that. But that's how you would find the starting and end points of them. All right. So this is my line segment in vector form. So I just want to run another poll. So it'll be A to D, A, B, C, D. Like, in terms of how this is going so far, just following the processes I'm going through. Like, fair enough, you might have to go in and learn formulas and stuff. But just in terms of following the processes and the calculations from A to D, how are we feeling? A being, I can follow them perfectly. D being, I'm very unsure. Okay, good. Hopefully I'm going at an okay pace. Okay. Okay, I'll try and maybe slow down just slightly again. All right, maybe I went through that one a bit quick. I'm also conscious that, oh, by the way, if you just joined in, you won't probably get it from Epson. They probably won't announce it, but there is the class Wednesday next week from 10 to half 11, but I'm also going to do one Thursday next week from 10 to half 11, just to try and do as best we can, all right? But that was 2A. 2b says find the intrinsic equation of the line segment. Now, there are lots of different intrinsic equations, but the one specifically that seems to be covered in this module, as I said, I wasn't sent your lecture notes. There's a lot in this kind of multivariable calculus, but from what I can gather, the only intrinsic equation that you deal with is in terms of arc length. So I can define, I'll try and keep it as brief as I can without theory, but I can define a line between here and here by saying, well, as if I'm traveling along this line, as time goes on, so let's pretend that this parameter t is time. I can say, well, as time goes on, I'm at XYZ position on this line. So if I sub in different values of t back here, if I sub in t is equals to a half, it might say after a half a second, I am here on this line segment. But I could also define a line by saying, if I travel a certain distance along the line, I'll be at that point. So it's just defining the line in terms of a different positioning system, essentially. So an intrinsic equation, they say like an intrinsic property of the curves and all that kind of stuff. But for this intrinsic equation, we're going to define our position on the line in terms of how far along we are, as opposed to how long has passed, essentially. So you have a formula for arc length, which is given here. It is a lovely looking formula, but we'll break it down and we'll try and take it one step at a time and see how we go with it. So, whoopsie daisies. There we go. So r-u, u is just a dummy variable here. It's not really important. We will integrate it with respect to u, but because this is a magnitude, you can see these two lines here, r-u should, in most cases, I won't say in every case, in most cases will just end up being a value anyway. So we have r of t. R of t equals x of t, y of t, z of t. We have found r of t. It was this thing here. Boom, that thing. That was our line segment. 3 plus 2t. 3 plus 2t. T. And 1 minus 4t. 1 minus 4t. For t between 0 and 1, that's still going to carry over. It's still just the line segment. T greater than or equal to 0 and less than or equal to 1. So that was our line segment. Excuse me. All right. Right. Is a vector equation of a piecewise smooth curve. This is that. We don't need to worry about that. The arc length S is defined to be. So we can see there's an integral, sure, right? But let's take this into account as well. For t between a and b. So my a value, I have my r of t below, and it's defined for a. So 0 is like my a value, and 1 is like my b value from up here. Right? That's how mine are being defined, because that's the start and end points of the segment. So S of t, my arc length, is equal to the integral between a and t. It's not a and b, a and t. So I'll be going between 0 and t. Okay. Of the magnitude of r dash u. Now, r dash means the derivative. So I can find the derivative of r of t. Find r dash t, because I have r of t. Differentiate these with respect to t. Differentiating a vector, you differentiate each component separately. So differentiate 3 plus 2t with respect to t. So 3 will differentiate to 0. It's just a constant. Differentiate 2t with respect to t, you'll just get 2. So differentiate 3, I get 0. Differentiate 2t with respect to t, I just get 2. Differentiate 1t with respect to t, I just get 1. Differentiate 1, I get 0. Differentiate minus 4t, I get minus 4. So that's our first derivative. The formula in the integral has the magnitude of the derivative. As I said, that r dash u, it's possible that it'll come into it, but because it's a magnitude, unless there's some other dummy variable in, it should just end up being a number. So the magnitude of r dash t, the magnitude of any vector, is the first component to be squared, plus the second component to be squared, plus the last component to be squared. Just throw that in a bracket because of the minus, and you take the square root of that. So I have 4 plus 1 is 5, plus 16 is 21. So that's the magnitude of r dash t. And let's go plugging stuff in. So I have the arc length as a function of t is the integral between a and t. Again, my a value, just by the definition up here, for a t greater than or equal to a, less than or equal to b, my a value is 0, up as far as t. The magnitude of r dash u, I know this is r dash t, but like, if I want to define the magnitude of r dash u, I would replace any t in that answer with u. There is no t in that answer, so it'll just be the same. So it's root 21 du. So I am now integrating with respect to u. If I integrate 2 with respect to x, I get 2x, plus a constant of integration if there's no limits. But if I integrate 2 with respect to y, I get 2y. If I integrate root 21 with respect to u, I'll get root 21u. It's just a constant. And I have limits of t and 0. So I've done the integration. I sub in my upper, when you have limits on an integral, once you've integrated, you sub in upper limit minus lower limit. So upper limit goes in instead of the variable, minus lower limit. So I just substituted in t instead of u for the first one, minus substitute in 0 instead of u. Root 21 times 0 is 0. So in total, my arc length function is that. Now, for the most part, we don't say s of t. We just say the arc length equals. So for simplicity's sake, I'll write that. Now, is that a question, or did someone leave? Someone left, let's say, or joined. So that's arc length as a function of t. S equals root 21t. What I said at the start was, what we're going to try and do with this law, instead of saying as time goes along, we're at this position on the line, I'm going to try and change that to as we travel along a distance, we're at this position. So the kind of, S equals root 21t. The whole logic of going around that is, I need to replace, I'll write it out again, sorry. I'll write out where we're at currently, 3 plus 2t. Like, this is our position in terms of the parameter t. I'm just pretending it's time. It could be whatever. This was our line segment in terms of t. I want to rewrite that in terms of arc length. So I want s inside in this as opposed to t. So I need to replace this t, this t, this t, and I also need to replace this t because I need to define the starting and end points in terms of arc length. But we'll come to that last. To replace these in terms of arc length, I'll just solve this for time. By my arc length workings, if I just divide across by root 21, I know that time equals the arc length over root 21. So substituting that in terms of arc length s will be 3 plus 2 times, instead of t, well, I know t equals s over root 21, comma, instead of that t, let's do the middle, the j coefficient, I'll just replace that directly. And then I have 1 minus 4 times t. And again, t in terms of arc length is s over root 21. So r of s equals 3 plus, well, 2 times s is 2s. So 2s over root 21 S over root 21 is the middle one, and 1 minus 4s over root 21. But that's the intrinsic equation of the infinite line, but I now need to get the starting and end points in terms of s, just like we did previously in terms of t. Simplest way to go about that, so I'll just start and end points here. End points. So instead of t being greater than or equal to 0 and less than or equal to 1, I'm going to pop in, well, t was s over root 21. I'll multiply across. So 0 times root 21 is still 0. So my lower s value will still be 0, but my upper s value will be 1 times root 21 is root 21. So let's say for s between 0 and root 21. So that would be your intrinsic equation. That if you Google that phrase, intrinsic equation, you'll probably be led to some Wolfram alpha thing, which gives you a whole blast of information. But as far as I can see, the intrinsic equation that you have to work out is to deal with arc length, and it's probably, you know, I'd expect that to be the one that you'd be working with. So that's it. That's question 2B. If you have questions before I move on to question 3, how are we doing for time? We're actually doing grand. My goal today was to do 1, 2, and 3. But any questions at this point? Bill? Yet? Okay, good stuff. Anybody else? Okay, doke. There's a few people typing there now. Question is asking and how to represent it. Absolutely. Like, thanks, Lisa. I actually was a secondary teacher. Maybe that's paying off. I don't know. That's my background as secondary teacher. Yeah, Michelle, just going back to what you were saying, the hardest thing is knowing what they're asking and what to go about. Like certain parts of these questions, like I don't know if you're teaching maths in schools. Maybe you are, maybe you aren't. I'm not too sure of the PDMT. I'm not too sure what the whole story is with it, because it's kind of an out of hours thing, and I don't see a lot of it. But the thing is with this, there are some questions in this kind of calculus tree, and if I'm not mistaken, you only had like 9 lectures or something of this. So there are some questions which will take, what should I say, applications. Your training. Yeah, I get the general gist of the program, but just in terms of how many weeks it is and all that, I'm kind of a bit out of catch with it. But there are some questions which will take applications, like work, maybe mass density, volume, and I'll be coming to them in the whole kind of double integrals, triple integrals kind of problems, right? But a lot of these, if you just look at the ones we've done so far, right? I'm trying to kind of get you into my thought space for it. Find the directional derivative at a point in the direction. Like you kind of have to be, I know it's hard because there are a lot of formulas in this type of material, but when I'm reading directional derivative at the point in the direction, I'm straight away writing down directional derivative and noting that's a unit vector and noting that del f is this. Straight away, I'm writing down that before I do anything else. It's kind of procedural. Yes, there is complex stuff to it. If you actually go to the lesson pages that I put up for you on our Solus site, I remember because it took me ages. I remember doing a video on what the directional derivative represents. There's like a video that rotates and it shows different things. So watch that if you want to get the whole image of what you're doing. But that in itself is kind of a procedural question if you know the formulas. So straight away, I'm linking that to those two formulas. Linear approximation. Depending on how many variables I have, this had of x, y, and z, I'm throwing in the whole lot of that formula that deals with x's, y's, and z's, up as far as the partial derivative with respect to z at the end. If you look at the paper just prior, just the one in, I don't know, when did you do exams in May or June? If you look at that one, it only went to x and y. So I wouldn't bother with this last part. I'd just leave that out, but I write the rest of it. And obviously I'd leave out the z's, zeros in these as well, because it only went as far as x and y. 3 tutorial based questions. Okay, 2 tutorials are online, 1 person. Okay. But again, straight away I'm writing down the formula for that one. Regardless of what the question really is, I'll deal with that afterwards. But formula has to be right first. The one just prior, I think, was quite a procedural one on linearization. This one, maybe not so much. I think that's kind of a tricky one, but should the likes of that come up, hopefully this makes sense, what I just did. As I said, if you are just joining, I'll be putting the slides up afterwards on our Solus site and MB5003 on the drop-down menu for that. Vector value function, it's a line, vector form of a line. I'm writing that down. And then I'll pick out my initial position vector and the direction I'll get by the end minus the start. Plug them in. If it's a line segment, you have to tell it where it starts and ends, like we just did for T. If it's a line that runs through both of those points, i.e. it doesn't stop at either of those points, it just runs through them. If it's a line, I don't need the start and end T values. I just say the line is 3 plus 2T, T, and 1 minus 4T. So that's vector form of a line. And then intrinsic equation, as check your notes, but as far as intrinsic equations go, I probably imagine that your intrinsic equations just deal with arc length. So instead of representing it as in terms of the parameter t, which, as I say, I have always imagined it as time, but it could be other things. But instead of interpreting or presenting the line segment in terms of t, I need to represent it in terms of s, in terms of arc length. So you solve for s, find out what that is by either one of these, depending on what kind of formula you're given in the question. Solve it for t. So t is s over root 21. Plug in s over root 21 instead of all the t's, and then define your start and end points. I know it's a lot. It's a lot, and it is. This content is quite abstract. I think. I think that makes it difficult. But so far, there has been phrases in the questions that I would be thinking, boom, write down the formula for that. Then deal with the rest of it afterwards. Deal with the workings afterwards. But the formulas have to be right and they have to go first. So I don't know if I've made things better or worse for you, Michelle, but that's kind of my take on it. Right. On to question 3. No worries, you're welcome. 3A has 2 different answers, essentially. I would say you write down both of these. So what calculation is to determine whether or not a vector field F is conservative? I'm not going to go into what conservative is. Possibly I'll put a video up for you in terms of rotations and things like that. Maybe I didn't record one, I can't remember, in the 24/7 help of what conservative is. But you need to know this. This is another definition. And actually in the summer exam from this year, I actually saw question 1A asked for a definition. Definitions take time to learn, but my God, they're brilliant if they come up in the exam, because it's literally state what the definition is. There is no workings needed. There's no calculations needed. So if you can have the time to put into learning them, they are brilliant as to come up as a question. And this is essentially asking for a definition. What calculation is used to determine whether or not a vector field is conservative? So a vector field F is conservative if the curl of F equals 0, i.e. del crossed with F, so cross product of del and F equals 0. or a vector field F is conservative if F equals to del omega. You'll see in my videos I use phi in the 24/7 because engineers tend to use phi for some scalar field omega. They're the same thing, omega and phi, but just engineers tend to use phi. So if you haven't checked out those videos yet, maybe they'd be helpful to do that. I think 8 people have watched them so far, engaged with them some bit. So they're there for you as well on our site if you want. But that's essentially 3-part A. 3-part B says consider a vector field F. We're given what that is. You can see that there's a vector, there's curly, or there's pointed brackets. We have a first part of it, we have a second part of it, and we have a third part of it. For some unknown component function R. So this one here, we don't know what that is. And we're asked, find a component function R that would ensure that F is a conservative vector field. Right? Choose the simplest option for R. Now, I just want to actually note one previous thing. Sorry, I'm hopping. But next short question 6 in summer exam. Yeah, so Celine, I'll be doing next Wednesday and Thursday. I'm also doing these classes from 10 to half 11, and I'll be continuing this paper. So I'll do question 6. That's the triple integral question. And I think the triple integral question then from this year's exam was incredibly similar. But I will go through question 6 from this paper. I want to give a lot of time to that because they're kind of messy. So I just want to note something here. If a vector field is conservative, it means F is irrotational. You need to know that. Irrotational, if I could spell this, irrotational. Because I think that came up in the summer exam. It says show that F is irrotational. Essentially, you were being asked to show that it's conservative. And if it's conservative, it means it's irrotational. Let me just give one quick glance at the exam from the summer. Maybe that was something else I looked at. Oh, it was in a tutorial sheet. Sorry. I did have a quick look at them this morning. Sorry. And this calculation will come into this question. I know that. Tutorial sheet 2, I think. Yeah, tutorial sheet 2 that you have, if I have the same version, under lecture 5 and lecture 6, video 1. Question 4 of that asks to define what is meant by a conservative vector field. So that's boom, that's that stuff that's up on the slide currently. Show that the vector field G, where G is a constant scalar acceleration due to gravity, is irrotational. That was the first part. So you were asked to show that it's irrotational, i.e. you were asked to show that this was the case. I'll be coming to that calculation. We'll be covering that now for this question, right? But that's what that tutorial sheet 2 question was asking you to do, was to show that it was conservative. And if it's conservative, by default, it's irrotational. All right. Anyway, sorry, that was just a side point. Now, find a component function R that would ensure that it's conservative. So I want to carry out this calculation and find an R that makes it equal to 0. So I'm trying to find this thing here that when I calculate this, it equals 0, right? So this thing, this is the curl. I'll write that down just for, oh, it's actually in the line above, sorry. That's the curl of F equals this. Now, the structure for this is we set up the determinant of a 3x3 matrix. The first 2 rows of this matrix will always be the same for curl. It's part of the formula for curl. By the way, just in case, any vertical lines around the matrix, just vertical lines signify the determinant of a matrix. It's not a rounded thing around the matrix or a box thing around the matrix. If you see vertical lines around the matrix, it means the determinant of that matrix. So I'll need more room between these because it's just a notation thing in case you'd maybe forgotten that. Space these out. First two rows always look the same. So they are the first two rows of the curl matrix. And in the last one, we put in, so technically it's like if this is a force, it's a vector field, but when it's F, I'm assuming it's a force field. F1 would be the first part, first component of the force. F2 would be the second component of the force, and F3 will be the last component of the force. So I'm just going to write those down for just if you look back at these later. That's what I'm going to be plugging in there, F1, F2, and F3. I'll take it down again, Fi, J, and K. I have, as I say, these ones are just set in stone for the curl formula. And now I'll plug in F1, which is the first component of the force, which is 3yz squared plus 2z. Z squared plus 2z. I'll plug in F2, which is 3z squared x minus y. And I'll plug in F3, which is that unknown thing R. As I said, it is the determinant. The curl is the determinant of that matrix. So just as a quick recap on determinants of 3x3 matrices, I'd like to do one just with numbers, but I'm just conscious of time. That just had numbers in the matrix as opposed to all the ij's and k's and stuff. The determinant of a 3x3 matrix, my advice to everyone is to mark plus, minus, plus across the top. That would be the first thing to do. Equals. I take a positive of that first entry, regardless of whether it's a number or whether it's I or whatever. I take a positive of that. I then block off the row and the column that is on, and I'm left with a 2x2 matrix, that bottom right hand side 2x2. I'll do it out step by step. So I have dy. No, I won't be doing all the determinants of 3x3s. I'll probably skip a few steps if they crop up again in the exam, but for now I'll do this one out. So that's my 2x2 matrix that I'm left with. So once I've crossed off the row and column for I then move along. And I might change the color for this one just for fun. I take a negative of that second entry. So whatever the second entry is, I take a negative of it, minus j. Same process, block off the row and the column that is on, and I'll be left with this, 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 and this. So I'll write that down in a 2x2 matrix. So I'd imagine that this would have been calculus 1 when you would have originally done this. If you want to look back on notes from that, it's probably there. Z and R. Last one we need to take care of is the K value, that third entry in the first row. So I take a positive of that value, whatever that value happens to be. Hopefully I'll fit it on this slide. Block off the row and the column, and I'm left with a 2x2 matrix here as well. I just write them down in the same order that they're in. Whoops. Y and 3y. Sorry, folks. That was horrendous planning in terms of space. Sorry. 3z squared x minus y. And vertical line around that. So now, instead of having the determinant of a 3x3 matrix, we break it down into, we have a couple of determinants of 2x2 matrices to take care of. So I'm going to move to a new slide. So I had plus I times the determinant of a 2x2 matrix. If they're just digits, we just multiply values. Whereas here, we can't really multiply these. It's del y we take the primary diagonal multiplied together. If these were just digits, I'd be multiplying those two values. When they're not digits, all I can really do is say del y of r would be that primary diagonal minus the other diagonal. So it's always for a 2 by 2 matrix, the primary diagonal minus the product of the other diagonal. So it'll be del z of this, of 3z squared x minus y. Essentially, both of those things are asking me first partial derivative with respect to y of r, first partial derivative with respect to z of that. Right? I have a minus j, and likewise 2 by 2. So primary diagonal del x of r minus the other diagonal, which is del. My handwriting there left me down big time. That was del z. That as it is usually del z of this. Of 3yz squared plus 2z. And the last one is a plus k. And 2 by 2 matrix del x of, big R for that one, 3z squared x minus y. Minus the other diagonal, which is del y of 3yz squared plus 2z, del y. So it's minus that other diagonal of 3yz squared plus 2z. Work down as much as we can now. So I del y of r. Remember, r is the thing I'm trying to find. I'm not treating r as if it's a constant. For partial differentiation, I kept repeating and repeating, we treat other things as constants, but r is an unknown thing. It's not a constant, not necessarily a constant. So I'm just going to leave that one alone. Del z of this. Now, here we have a known function, a function that we do know. So I'm going to partially differentiate that with respect to z, treating x and y as constants. So differentiate 3z squared x. I'm treating x and 3 obviously as constants. So the z squared will just multiply down as usual. 6 reduced power by 1. The x constant will be there as well. Minus y, well, when I'm partially differentiating with respect to z, I'm treating y as just it's a number, like minus 4. So that will go to 0. So that'll be my first one. Likewise with this, I don't know what r is. I'll actually throw it up here. I can throw it up here on the top. Matter. Minus del z of this. So the y I'm just treating like a constant. I'll multiply down by my power. So it'll be minus 6yz with respect to z. Minus by plus 2z is minus 2z. So when I differentiate minus 2z with respect to z, I get minus 2. Differentiate this with respect to x. I know the y will go to 0 because that's going to be treated as a constant. Differentiate 3z squared x with respect to x. I'm treating 3z squared. Z would be treated like a constant. If I differentiated, what's that? 12x, I'd be left with 12. So I'll just be left with 3z. Or sorry, 6z. Whoops. Nope, 3z squared. That was right. The x term will go essentially. When I'm differentiating x with respect to x, I get 1. So I'll just be left with 1 times 3z squared. Differentiate minus y with respect to x, I get 0. Differentiate the next one with respect to y, just run the bracket. So 3z squared are like constants. If I differentiate any constant times y, I'm just left with the constant. So I'd be just left with 3z squared. Differentiate 2z with respect to y, I get 0. 3z squared minus 3z squared will cancel. They give me 0k. Now, going back to the question, I might have left that somewhere in the lurch there. We're asked to find R such that vector field given is conservative. What I said was, it's conservative if the curl, so this calculation that we're just going through, if that equals 0. So this will be conservative if the curl, which I have up here, it's a bit messy. I'll try to rewrite it a bit. 6zx minus j times. If all of this equals 0, it will be conservative. Plus 0k. I.e., if that equals 0i plus 0j plus 0k. So it's conservative if all of that calculation that we've just gone through, see that, it's conservative if all of that calculation is 0, i.e. 0i, 0j, 0k. By that, just matching the coefficients now, we've done something like this, a while ago. We had a matching coefficients kind of situation. Like the I coefficient is this, it's I times that. So if that equals 0, and the next one, the j equals 0, this equals 0. I mean, the k, I can just see 0 is 0, so I can't do anything with that. But if the j coefficient equals 0, so we have two equations there now where we're going to try and find R out of them. These are, if you want to look up what topic it is from this point, these will be first order PDEs, partial differential equations. More likely a calculus 2 thing if you've covered them previously. Go pick up, kids. No worries, kid. You're very welcome. Hopefully I'll see you next week. This probably is a calculus 2 thing. Minus 6zx equals 0, sorry. If you've covered them previously, or maybe you covered them in this module. I'm, as I said, the PDMT one, just not sure of all the syllabus of all the modules in PDMT. Minus 6yz minus 2. 0. So we're going to try and solve these first order PDEs. I'll try and do a partial differential equations. We're going to try and solve these for R, because that's what we're looking for. So let's go ahead and try and do it. We can isolate R here, or dr dy I should say, be equals to plus 6zx. Is that a question or someone leaving? I think there's someone leaving. I'll do the same with the other one, just the algebra side before we do any more. So that'll be plus 6yz plus 2. Hopefully I haven't made any arithmetical errors as far as there. 6yz plus 2. No, on the right track. So we're looking for R. Now, if this, I mean, that says the first partial derivative of R with respect to y is 6zx. Now, I'm trying to find R. I need to reverse that derivative. How do we reverse derivatives? How do we go backwards? That is integrate. Exactly. Integration and differentiation are the reversals of each other. If I started with R, for example, R is some stuff, 2xy, I could partially differentiate that with respect to y if I wanted to. If I want to reverse this, I need to integrate this partially with respect to y, right? Because I'm trying to get back to R. I need to integrate this with respect to y. Okay? To reverse a derivative with respect to y, to reverse that, I need to integrate partially with respect to y. Right? So let's bear with me with this one, best you can. So when I'm integrating with respect to y, again, I'm treating x and z as constants. So if I integrate, easier example, I should say, 3 with respect to y, I'd get 3y. Yeah? So if I integrate 6zx with respect to y, I'm treating x and z as constants, I'll get 6, put them in alphabetical order, 6yz. I include a y, just like here I included a y. All right? We're almost there. Almost there. I'm going to take our answer there as a starting point, and let's partially differentiate that. I mean, this should be able to be reversed again, right? If I differentiated this partially with respect to y, I should get back to there. So let's see what happens. If I differentiate this partially with respect to y, treating x and z's as constants, if I have some constant times y, I'll be left with a constant. And perfect, that looks grand. Brings us back to the same point. However, if I added on 3x plus 2z onto this and differentiated them partially with respect to y, they would both go to 0. So this would also work for this equation. Now, how do we attend to that? What I'm going to do, I'll explain this in a second, is I'm going to add on a function of the other variables. Because if I partially differentiated this with respect to y, sure, the first term, 6yz, will give me this one here. But if I differentiate a function that just has x's and z's in it, it might be the sine of xz or something mad, e to the x plus z plus 3z squared. If it only has x's and z's in it, they're just constants. So that would, with respect to y, partially differentiated, would go to 0, which would still align up with that. Hopefully that makes some bit of sense. Right? But it tends to be, in terms of partial integration, it tends to be a real kind of, what the hell is that doing in there? It looks totally random. But that's why it's there. It's because if you go reversing that process and partially differentiate this with respect to y, any function that just has x's and z's in it will just be a constant function, so it will go to 0. Hence why it has to be there in the bottom line there on the left-hand side. So hopefully it makes some bit of logic why it's there. Because it can be a thing when you're looking through solutions and you see these functions thrown in, people go, where did that come from? And we're going to see something very similar here. Remember, we had another equation as well. If this is the first partial derivative of r with respect to x, I'm going to need to integrate this partially with respect to x to go backwards, essentially. All right, to reverse that process. R will equal integrate 6yz with respect to x. I'm treating y and z as constants. If I integrate 5 with respect to x, I get 5x. So if I just have constants with respect to x, I'll get 6xyz. Just an x will be thrown in with the constant. Integrate 2x with respect to x. So 2x is just a normal x function. So what do? We use our power rule. We add 1 to the power to integrate and divide by the new power. Those will cancel. Right? That's my integration done. Where did RGAT2x? Where did RGAT? I know, just trying to do this 2x. Oh, whoa, thank you. That was just 2. My bad. Sorry, this just said +2. I'm integrating 2, not 2x. I don't know why I threw down 2x. Thanks for that. I would have mucked things up. So integrate a constant 2 with respect to x, you get 2x. Thanks for that. So that's our R. But because this is partial, I will need to add on some, I'm not going to say f, I've already used f. Let's say g of y and z. So some function that just has y's and z's in it. Because if I partially differentiate with respect to x, a function that just has y's and z's in it, it will go to 0. So it would still, all of that, I mean, partially differentiate that with respect to x, I get 6yz. Partially differentiate that with respect to x, I do get 2. Partially differentiate some function with just y's and z's in it that I'm treating as constants, it would go to 0. So that's why you're going to see these functions added in. Now, to find R, basically, we need to find an R, said the simplest one, that satisfies this and this. So essentially, we're going to combine both of those. Plus f. So this was the first one. And the other one was 6xyz plus 2x. Plus some function of y and z. Okay. So we're going to need to satisfy both of those. So combining them, I can see that 6xyz is in both, so that has to be there. There's plus some function of x and z. The 2x will do that job. I know there's no z in it, but f of xy, for example, can equal just, f of xy can just equal a constant if you want. It doesn't have to have either of the variables in it. Like you'd often see straight lines, like horizontal lines, f of x equals 4. It doesn't have to have the variables in it. So I can take this, fill the place of this one. And then g of yz, there is no function in this first one that just has y's and z's in it. So I can just say that that's 0. Leave that out. My advice to you at this point is, because I know that can be a bit, people say, well, why is that 0? Where has that been left out? Include any terms that are in both of them. Be the way I'd put it. Or include any terms that are certainly in both of them, like the 6yz, but then if you have the likes of 2x, include that as well. If there's nothing else there, just leave it out. Now, I think we have, why are we out of time? Yeah, I don't really want to, I think that's probably enough. I tell you what, I'm going to put it to the group and say, yes or no, do you want me to finish question 3? Assuming then there might be less time for question at the end of next week, next Thursday's one. I'm doing Wednesday and Thursday. Do you want me to finish question 3 today? Yes or no? I won't be offended if you say no, but go with the majority. Okay, I'm going to finish question 3 today. Sorry if you said no, but I will continue with it because that's what the majority have said. So that's our R. But what I do advise you to do next week, or before next week, or maybe straight after this, is, do you remember we said that choose an R that would make it conservative, or that would make it irrotational, if you want to put it that way? What I'd advise you to do is throw in the R that we just found at the end. R was 6xyz plus 2x, I think. Throw it in here, and when you work out the curl, it should equal 0. It should be conservative. Right? So that's just a little check. If it's always good to check things when we can. Okay, so for G equals, now this is part 2, F is now the B part 1 with that R filled in. So I'm going to write out what F is. As given in the question, we were told f of xyz was 3yz squared plus 2z, squared plus 2z, 3z squared x minus y, comma, R, which we just found, which was 6 xyz plus 2x. That was f. That's going to go in here. Here. And we're going to subtract that one. Might as well do that first and just determine what g actually is to begin with. So g of xyz is f of xyz, which is that one just above. I'm going to save myself some writing here because some people, I'm sure, have other things to do. You're on summer holidays now, aren't you? So it'll be f of xyz minus that other stuff in the question. We were told it was f minus that. So g of xyz, to subtract two vectors, first component minus first component. So I'll have 3yz squared plus 2z minus 2z will cancel. So that's the end of that one. I have second component minus second component. So I have 3z squared x minus y minus minus y. So minus minus y is plus y. So minus y plus y will cancel. That's the end of that one. I have 6yz minus 6xyz. 6xyz minus 6xyz would cancel. So I'll just have 2x left in this. So that's the g thing that I'm given at the top. That's the vector field that I'm working with. We're asked to determine the work done by the vector field g in moving a particle along the line segment from 1, minus 1, 0 to 2, 1, 1. The work formula that you're given, now that might change. That might be f if it was f, but here the question says for g, so I've said g. Dot dr. C is the region that you're working on, right? So C here is the curve, i.e. the line segment that we're talking about moving it along, right? The way to go about these are called line integrals. If it's a single integral, it's called a line integral. The way to go about these is to parameterize the whole thing. So we're going to parameterize the line. This is the same process as, remember when we found the vector value function for the line segment? This is exactly the same as that. Actually, now that that's done, considering that, is that what this line was? Is it the same one? No, it's not. So we have to do this again. It would have been handy if it was the same. We could have just used that one. But anyway, I have to parameterize this line. So R of t, little line, segment. Again, segment meaning we need to give a start and end point for this line. So it's, I'll do it quickly. I'm not going to do the same rigmarole. So it's our initial position vector plus the direction vector, which is 2 minus 1. Remember, second vector minus the first. 1 minus minus 1 is 1 plus 1. 1 minus 0 times t. That's 1 minus 1, 0 plus 1 times t is t. 2 times t is 2t. 1 times t is t. And lastly, we'll just combine those. So 1 plus t minus 1 plus 2t and 0 plus t is just t. It's a line segment. So this will start, I mean, the easiest one to look at is the last one because it just has t in it. Hold on. It will start when that value there is 0. As I said, you could solve either of the other ones too. If you took the first one, hopefully you can see my cursor on that, can you? I think you can. 1 plus t, you could let that equal to 1 and solve it for t. You could take the middle one, minus 1 plus 2t, let that equal to the middle one, minus 1, and solve that for t. But the last one's the easiest one to go off because it just has t in it. So t will definitely start at 0 and it will go up as far as when that t value is 1. So again, for t greater than or equal to 0, less than or equal to 1. They'll be our parameters for t. Now, I'm sure the next formula that I'm going to write up is in your notes as well, right? It's the parameterized version of this. Well, I'll scribble it down up here. So it would be, what's next? I'll keep to year notation because I might write this a bit differently. So I'd have t values, t1 and t2. This is the parameterized version just with t's in it. G of t. So I'll have to write g as a function of t alone dot r dash t dt. Now I have r of t. That's the curve that I'm going along. So I'll be able to find that by differentiating r of t. T1 and T2 are the parameter start and end points. I can see that t is between 0 and 1. We've worked that out. So T1 will be 0 and the upper limit T2 will be 1. So have them. I'll be able to find this and then I'll talk you through doing that as well. But the approach is, I mean, from the starting point, why am I saying to parameterize it to begin with? Why in the hand of God are we doing all this? It's because if I left it, let me just change up the color. If I left it at this, for example, G will have X, Y, and Z's in it. DR is like a unit thing in terms of a parameterization, so that's not going to help. But we do a single integral with X, Y, and Z's in it. There's no way to do that. You can partially integrate, but you can't integrate. So we have to change it all. So what I'm actually doing is I'm changing everything to be in terms of one variable with the limits for that variable in the limits, as opposed to having X, Y's, and Z's and stuff. I'm just changing everything from X, Y's, and Z's to just T. Okay, so that's why I'm doing it. But anyway, R dash T, we need that for our formula here. So I differentiate, there's R of T with respect to T. I'll just rewrite R of T to begin with. Or piece of readability afterwards. So R of T we simplified down to this. So I find R dash T, I'll differentiate that with respect to T. Differentiate 1, you get 0. Differentiate 1T with respect to T, you just get 1. Differentiate minus 1, you get 0. Differentiate 2T, you get 2. Differentiate 1T with respect to T, you get 1. So that's R dash T for up here. Now, G of T is still something I need to find. So I'm going to write down G of X, Y, Z. We did simplify, thankfully, because it looked miserable in the line above. So G of X, Y, Z equal to 3YZ squared, 3Z squared X. YZ squared, Z squared X, YZ squared, Z squared X. Yeah, 2X. So that was G of X, Y, Z, and I'm looking for G of T. I just want to check, was there a question that binged, or oh, people are probably having to head away. Sorry, young folks, if you do. But let's go back, and so in our line, we're going to try and combine the two things now if we can. Like, here's our line, and a line is parameterized. I actually think it's in one of the previous formulas. Hold on a second and we'll see. Yeah, so if R of T, there was a parameterized version of the line, is X of T, X as a function of T, Y as a function of T, and Z as a function of T. That's how just the general vector form of the line would be. It'd be the X, Y, and Z. So combining that idea here, so I'll write out R of T again. Remember, R of T was X of T, Y of T, Z of T. So the X is 1 plus T. The Y is minus 1 plus 2T. And the Z is 1T. So I'm going to, in order to transform G of X, Y, Z into just G of T, I'm going to be replacing any x's in g of x, y, z with 1 plus t. I'll be replacing any y's in g of x, y, z with minus 1 plus 2t, and I'll be replacing any z's with just t. That will give me g of t. It will get rid of any x, y's, and z's, and will replace them with a single variable of t. So I'll have 3 times yz squared. So y times z squared, t squared is just t squared. I'll have 3 times z squared, is t squared, times x, which is 1 plus t. And I have 2 times x, which is 2 times 1 plus t. But that's what I'm going to simplify that, but that'll give me g of t. So I have 3 times minus 1 times t squared is minus 3t squared. 3 times 2t is 6t times t squared is 6t cubed. I have 3 times t squared times 1 is 3t squared. 3 times t squared times t is 3t cubed. And lastly, I have 2 times 1 and 2 times t. So that's g of t. So we can go back now, go back to our work formula. As I said, I'll write out the parameterized version. And we can fill in all of that stuff that we have. So T1 and T2 are the initial and end parameter points. I know that T has to go between 0 and 1, and along the curve that we're on, along this region that we're on. The curve is the line segment between 0 and 1. So the work will equal the integral between 0 and 1. There are t values. G of t is all of that thing that we just worked out. Whoops. Dot r dash t. A dot now is a dot product again, so that'll be 2 vectors dot producted together. R dash t was 1, 2, 1 at the very bottom of that slide. Thankfully, that doesn't have t's in it and all that kind of stuff. dt. So we're integrating with respect to t. Definitely going to do the dot product first. So it'll be that times 1. Remember, dot product, I by I plus j by j plus k by k. First component by first component. Well, anything times 1 is just itself. I'll just leave it as that. Plus 3t squared plus 3t cubed times 2. I'll do that out. Look, they're just multiplied by 2. So 6t squared plus 6t cubed plus k by k. So 2 plus 2t times 1 is just 2 plus 2t. Again, dot product shouldn't give us a vector as an answer. It should give us a scalar. Dot product or scalar product are the same thing. So I'm not getting a vector. I'm just getting a polynomial back, cubic in this case. So work equals 0 to 1. Whoops. 0 to 1. We'll tidy up whatever we can. 6t cubed plus 6t cubed is 12t cubed. Notice now, it's just that single variable, and I'll be integrating with respect to that same variable. That's why the parameterization has happened. Minus 3t squared plus 6t squared is plus 3t squared. And I still have a 2 plus 2t at the end. There's nothing else to combine them with, so I'll just leave them 2t plus 2 with respect to t. Now I'm integrating a single integral with respect to t. They're all in t already, so I'll just carry out my power rule for integration. So integrate the first one, add 1 to the power, divide by the new power. Second one, add 1 to the power, divide by the new power. Add 1, so that's 2t to the power 1, so add 1 to the power, divide by the new power. Integrate a constant with respect to t, you get constant times t, and I have limits of 1 and 0. 4 into 12 goes 3 times. I'm not writing this out again, but 3's will cancel, the 2's will cancel. So limits now, I have the integration done. I substitute in my upper limit. So I have 3t to the power of 4. My upper limit is 1. So 3 times 1 to the power of 4. My upper limit going in. I'll have 1 cubed I'll have a 1 squared, and I'll have 2 times a 1, upper limit, minus the lower limit. So I have 3 times 0 to the 4, plus 0 to be cubed, plus 0 to be squared, plus 2 times 0. Now, some people do not sub in zeros, always sub in zeros for limits, because if it was the cost of something, cost of t, that wouldn't go to 0. If you had a constant in this bracket here, and you sub in 0, the constant wouldn't disappear, it'd still be there. So never just say, oh, well, one of them 0, so I'll forget about it. Always sub it in, is my advice. But it's a silly mistake. If it can be avoided, you might as well. But here, they do happen to be 0. So 3 times 1 is 3, and 1 is 4, and 1 is 5, and 2 is 7. So the work done would be 7 units of work. Sure, some of you are science teachers, maybe. I don't know. What's that? Joules? That work? I can't remember. But 7 units, it would be the work done. All right. So that's question 3. Just before I leave you, I've gone well over. I'm very sorry. It happens to me at times. Let me just see what the kind of work came up. Yeah, so if you look at the paper just gone, in the summer just gone, question 4 in that was worth a lot of marks. It was worth 13 marks. You were given a force field. You didn't have to work out G. Like, remember, we had to work out a force that was conservative and all that stuff. We had to find an R, sorry, that would make it conservative. You're given a force field. You're told where the particle moves along a curve. So again, you have to parameterize. That's a parameterization problem first. Just look at the solution. I imagine it'll be very similar to what we just did there, just that the curves might be a bit more complicated. But what I'm trying to say is that if you go to the solutions now, pending that you have the solutions, maybe following them will be okay. Because sometimes stuff just comes out of nowhere in solutions. I totally get that. I'm not immune to that. Yeah, I'd strongly advise up through the solution of that. Can you understand where each line came from? And can you understand why it was done? But it's a similar problem to this. The workings are more complicated because you didn't have to do the first part of this question that we did. But at the same time, I think they're okay. The logic of what I just covered here is still the same. I'm not going to do any more today. I was asked to do question 6 next week. That's all that really came in. I absolutely will be doing question 6. We'll be finishing this paper for sure between Wednesday and Thursday next week. If you have joined in late or whatever, I'm also doing Thursday next week from 10 to half 11 because I don't think it would do any harm. And it will allow me to cover some of more of the background stuff when it comes to triple integrals and that I'm not rushing, because as I said, no one wins if I rush. No worries, you're very welcome. Hopefully that was helpful. If you have comments or whatever, send them on. I'm off for the rest of this week, so I will get back to you on Monday. But if you have comments, questions, you can email them on. There isn't that many people here, so all right, no worries, you're welcome. No problem. I'll see you next Wednesday, hopefully. Oh, sorry, someone asked about slides. Yep. Hopefully you're still there, John. You haven't left. I'm putting the slides. So if you go back to our Solus site, so Big Blue Button should be a new tab. If you go back to another tab to see our Solus site, if you scroll down the left menu of that, I built 3 pages for MB5003 last week, just based on what I had on file, because literally the request came in the same day I made them. That was when Epi7 contacted us to see if we do something. It's on the MB5003 24/7 support drop-down menu of our Solus site. Currently, there's 4 subpages. Straight after this class, I'll add another one called revision slides, maybe something along that line, and I'll put the slides into that subfolder there. All right, so that's where I'll put them. The summer paper that I mentioned, were you given? Yeah, so somebody asked that. I don't know what you're given versus what I'm given. The summer paper from just the summer gone past, do you have that? I can't send it to you, unfortunately, but you do. Okay, so Michelle, is it? So Michelle, Monica, do you mind maybe just quickly where you could find it? On Solus or on the drive? Okay, on the drive. Is that a OneDrive folder, or a shared OneDrive, is it? Or?
Richard, it's a Google Drive that we have, but I don't think you well know that we have the Google Drive, so say nothing.
Okie doke. That's your own study business. It's nothing to do with me. Or share Google. Right. Well, look, if you even whoever asked, if you have that, great. If not, if you email the lecturer, if it was sent out, then I'm sure there'll be no problem with that. But anyway, look, I'll see you next Wednesday, folks. Take care. If you've questions, comments, if you want me to slow down, if you want me to cover back some stuff maybe prior, I might have videos on like some of the background stuff, like more the kind of basic integrals than what we've been doing here. I'm happy to forward you links to videos, or I'm happy to answer whatever I can via an email. It's impossible to answer maths usually via email. Genevieve, yeah, you can, but it's impossible to answer through email. But I will try to consider whatever comes in and maybe add that on next Thursday. If I had just a kind of a couple that I might be able to fit in, I'm happy to do whatever. All right, I'll do my best. Okay, folks, I will see you next week. Have a good week.